Welcome back, Calculus. We are looking at sample test 2 still. Now we're in the multiple choice, the calculator section, numbers 29 through 37. The second video will go through numbers 38 through 45. So let's jump right in. When we look at this at number 29, it says if f is a function such that we have this piece right here, which of the following must be true? Well, this is a limit that we're looking at, but it's not just any limit. This is another form of the definition of derivative. And what that means is that I'm really trying to find what this means in terms of just as a function. So this right here, if I were to rewrite that, limit as x approaches a of f of x minus f of a all over x minus a. We're really looking at the slope as x and a get really close together, so that's called the instantaneous slope. That's the instant slope. And if that's the instant slope at a, then this is really f prime of a. In other words, that's saying right here up top that f prime of a equals 0. Well, if f prime of a equals 0, let's see which one of these statements must be true. The limit does not exist. Well, we don't know. Maybe. F of a does not exist. Well, no, I don't think that's true. F prime of a equals 0. That is our winner. F of a equals 0, that's definitely not true. And f of x is continuous at x equals 0. We have no idea because this is not talking about x equals 0, it's talking about x equals a. So a and b shouldn't be true actually, because these both have to do with continuity, and for you to have a derivative you do need to be continuous, so those should be actually false. And C is true because that definition of a derivative is translated into f prime of a. Alright, let's do the next one. So this is a graph of derivative. It's got twice differentiable. It says f of 1 equals negative 2. Which of the following is true? So right here, this is telling me that y equals f prime of x. This is a first derivative. Okay, and notice that it's negative down here, and then it's positive up here. So if I were to sketch the original function, let's take that back, make it a cleaner line here. If I were to sketch the original function, it says f of 1 equals negative 2. Draw this in blue. So f of 1 equals negative 2. That means I'm down here somewhere. And since this is a negative slope, that means I go down until I flatten out at 2. And then I come back up. And I think I'm probably going to go a little bit higher than I originally started. But let's see what we're looking at then. F prime of 2, well, that's going to be 0. F of 2 is going to be less than that. That is for sure true. So either A or D are true. How do I know that's true? Because it's decreasing from here to here. And if f prime of 2 equals 0 and f of 2 is less than 0, well then it's got to be less than that. So the only thing that we're trying to look at then is, does it work such that the concavity is also negative, or is the concavity positive? Well, if you look at this function the entire time, the concavity is concave up. Therefore, we're looking at A would be our answer. Because concave up means that if something's concave up, that means that the second derivative at that point is greater than 0. So here we have a 0, here we have a negative for the original function, and the second derivative is positive. So A would have been our answer. Let's look at number 31. It says this function is everywhere differentiable, given for several values of x in the table below, and is always increasing. Which statement about f of x must be true. Now notice again that the values that they're giving us is the derivative, so we're talking about slopes here. Let's see how we can relate that to the information below. F of x has a relative minimum at x equals 0. Well, if we're looking right here at x equals 0, oh, by the way, f prime of x is always increasing. If f prime of x is increasing, that means that f double prime of x is greater than 0. That means that we're concave up. When one function is increasing, that means its derivative is positive or greater than 0. So we are concave up. F of x has a relative minimum at x equals 0. Well, that seems to be true here because we're negative, then we're 0, then we're positive. Maybe that could be, that's a possibility. Let's look at B. F of x is concave downwards for all x. No, that's definitely not true because f prime of x is always increasing. F of x has a point of inflection at 0, f of 0. Well, it's kind of weird. It couldn't be a point of inflection necessarily because that would mean that the slopes would not change and they wouldn't be increasing. That would mean that at some point they'd also be decreasing. The f prime of x would actually have to change direction. It couldn't always be monotonically increasing. So C, that one's out. F of x passes through the origin. Well, actually we don't know. We have no idea. There's no way to tell because we don't know anything about the original function. We just know about its slopes. F of x is an odd function. Again, we need the original function for either D or E to be able to be figured out. So it must be A. The answer is A. Moving on, number 32. A certain species of fish will grow from x million to x times 15 minus x million 1 year. So there's a delta here. Delta y equals this amount. In order to sustain a steady catch, a limit of million, blah, 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 million fish are to be caught, leaving x million fish to reproduce each year. What is the number of fish which should be left to reproduce each year so that the maximum catch could be sustained from year to year? And this is a long, wordy question, but it says that the catch each year, the catch, which is our function, is equal to this difference here, x times 15 minus x, and then minus x again. So then what it's asking us to do is to maximize that catch. We want to have a maximum catch. So if our catch function, let's call it c of x, is this, how do we maximize that? Well, we take the derivative. C prime of x is going to be, well, this might be a little bit easier if I distribute things. We'll have 15x minus x squared, and then minus another x. So that would turn out to be 14x minus x squared. So c prime, the first derivative, is going to be 14 minus 2x. And if I want to find a maximum of this, that means I need to set this equal to 0, find my critical points, and then work my way from there. Because 0 is going to be that flat maximum spot that we hit. So 0 equals 14 minus 2x. We solve this, and we get 2x equals 14. X equals 7. Well, I need to confirm that this is actually a maximum and not some other weird value, but I can be pretty sure that my answer is going to be B. But just to confirm it, let's see what would happen. If I'm at 7, I just need to pick a couple of numbers before and after. So let's say 5 and 8 works for me. Let's make this cleaner again. Let's move to some gray lines here, some horizontal lines. So now what we're doing is we're comparing these values. Let's make this middle one a different color just so we can differentiate a little bit. So we know at 7 that it's 0, but let's see what happens at the other numbers. At 5, if I were to plug in 5 into this original equation, 4 minus 2 times 5 is 10. 14 minus 10, that's 4. That's positive. If I were to plug in 8, 14 minus 2 times 8 is 16. 14 minus 16 is negative 2. That's negative. So that means that I'm going up, then I hit a flat spot at 7, and then I'm going down afterwards. That's definitely going to be a max because I changed from increasing to decreasing, or a positive derivative to a negative derivative. So I know that's true. Let's keep moving on. The next one, the figure above shows a graph of a function which has a horizontal asymptote at y equals 3 and y equals negative 3. Which of the statements must be true? I didn't include the multiple choices in here, but we can work our way to the answer just from these. Okay, it says f prime of x is less than 0. So if this is a function, the original function, it's what number 1 is saying right here is that no matter what x is, as long as it's on the right side and it has a horizontal asymptote here, that it's going to be a negative slope. That looks true. We don't know if this actually goes up and then comes back down. It's possible that it could, but it looks true for the most part. Let's see what else we have here. The limit as x approaches positive infinity of the derivative has to equal 0. That is definitely true. Why? Because we have a horizontal asymptote. We have a horizontal line near infinity. And if that's the case, then we know that the slope is going to be flat, and the derivative represents the slope, so that second one is for sure true. Number 3, the limit as x approaches negative infinity of f prime of x equals 3. That's for sure false. So 3 is for sure false, 2 is for sure true, 1 is a maybe. So I'm going to say that 2 only is true. Now, if there's only options with 1 and 2, then we can include that one in. But I would be willing to argue that we don't know about this area out here, and this could be a positive slope later on. We don't know that. We just know eventually it gets flat. Let's look at the next one. Okay, this one's got a lot of interpretation here, but let's look at what we're being asked. It says, which of the following could be the graph of the derivative of f of x? Well, let's figure out how we could get f of x from our original piece anyways. This is g of x, and we know that g of x equals the integral from a to x of f of t. Well, if I were to look at g prime of x, if I were to take the derivative of this piece here, by a fundamental theorem of calculus, that would just become f of x, because the derivative of the integral is going to undo itself, and then we have a constant bottom, just x on top, so it's just f of x. Then that means that g double prime of x is actually going to be our derivative, f prime of x, or the derivative with respect to x of f of x. So that means we're looking at g double prime of x to interpret f prime of x. Well, g double prime of x would represent the concavity or second derivative of this original picture. So we're looking at the concavity of this picture. So I'm going to color this in a couple of colors here. If we look at this area that's green, this is concave down. And then right here in the middle, let's make it red. That's concave up, looks like about there. And then we go back to concave down. So since I color-coded those pieces, this red part in the middle, that's going to be our positive, and then the greens on either side, that's going to be negative and negative. So our function should be negative on the left and right and positive in the middle. The only one that even comes close to that is B. A has some curves to it, D has some curves to it, E does. C might have been another candidate, knowing that the concavity is different in the middle as it is on the outsides, but it's upside down. So B is the only one that really makes sense. But remember, the thing that led us to that is realizing that by fundamental theorem of calculus we could relate g prime of x and f of x, and that allowed us to go to the next step, which was saying that the second derivative of g is related to the first derivative of f, which is what we're really being asked about on this interval. Let's look at the next one. Number 35. The graph shows the distance s of t from a reference point. So each of these represents a distance of a particle moving on a number line as a function of time. So here's its distance, and here's time. So it starts very far away, it gets a little bit closer, and then it goes further away, and then it gets closer again. Which of the points marked is closest to the point where the acceleration first becomes negative? Okay, if we have s of t, s prime of t, which is our slopes of this, is equal to velocity. And then the second derivative is going to be equal to our acceleration. So we want to look at second derivative. And if we're looking at second derivative becoming negative, that's when second derivative, or acceleration, is going to become negative. That means the concavity is down if s double prime of t is negative. So we want to see, when does the concavity first change down? Well, up. Let's do some color coding again. I'll do blue for, well, let's keep it the same. We got red for concave up. So we're concave up, we're happy, we're smiling, and then right about when we hit C here, we change. So that means C would be that point when we first become concave down, or S prime, double prime of t is less than 0. So right here in the middle at C. At C. And I'm guessing that the choice was C for C. Next, we have a function. The derivative of f is given by f prime equals this. At what value of x is f of x an absolute minimum? Well, we are going to need a calculator, clearly. We have some things that we need to solve here. But if we're given the first derivative, let's go ahead and plot that on a graphing calculator. So let's go to my y equals here. We're using the inverse of natural log, so it's going to be second e to the x. Then we're going to multiply. What was that other piece there that we need? It's e to the x times negative x cubed plus 3x. So we get negative x to the third power plus 3x. And then we have another constant on the end of that. It's minus 3. Now I know in the window it was saying that we go from 0 to 5, so let's go ahead and set that up. I have no idea what my y values are going to be, but I'm going to find out in a second. Well, it looks like if this is our derivative, we got two choices. It's either this number that's right before 1 or this number that's right before 2. So as I'm looking at this, excuse me, I noticed that I changed from negative to positive here just below 1, and I changed from positive to negative here right before 2. So if I were to visualize that, and we have this number line, and the graph kind of looks like this. And we got a 1 and a 2. This is a 1 and a 2. So down here, f prime is negative, then it goes to a positive, and then it's positive here, and then it goes down to negative. So that means that our original graph was down and then up. And then here, we change from positive down to negative. So we're asking ourselves, when is it an absolute min? The only place that would actually make sense is right here. Now, one keyword, actually, and I shouldn't say the only place that actually makes sense, it says the absolute min. How do we know if it's at an absolute min at that point? Well, the only way that we could tell is if we could see how much further down this piece goes here, and if we knew what happens there. But let's take a look at the graph, see if we can reinterpret that. So we have a negative slope, and then we're positive, we're increasing, 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 then we come back down, and then we're decreasing. And we continually decrease the entire time. The entire time we're going to be decreasing. Well, that means that maybe we actually went below that. We went below that value. Then the absolute min would be right here at 5. So even though this is a relative min, the absolute min is probably going to be here at the end point. And that would actually kind of make sense. So the absolute min on this interval would be here at 5. Okay, let's check the next one. The table above gives a value for a differentiable function. What's the approximate value of f prime of 4? F prime of 4 is approximately going to be really close to the slope near 4. So all we really need to do is find something that has like the slope of f of 4. Or let's do this, f of 4.001 minus f of 4 over 4.001 minus 4, which would equal, well, on the bottom we're going to have 0.001, and on the top f of 4.001 is 1.16016, and we're going to subtract from that f of 4, which is 1.15782. We're going to divide all that by 0.001. Well, let's go ahead and pull our calculators out. See if we can shrink this left to right. Maybe give ourselves a little bit more space so we can see what's going on here. So we have, let's clear this graph, go back to just some calculations. 1.16016 minus 1.15782. That's our numerator. We're going to divide that by 0.001, and you should get about 2.34. So as long as you have a slope that's somewhere around 2.34, that would be your answer. I don't have the actual choices here available, but the answer that I get is around 2.34. And you could have used multiple pieces for that. I did the slope between these two numbers here. You could have done between 399 and 400. It really doesn't matter, but you just need it near 4, because f prime of 4 is the slope near 4. Let's look at 38. Ah, that's it. We'll continue in the next video.